The optical fibers that we send light down are actually thinner than one strand of hair.
For the first time, we've demonstrated that you can take silicon and laze with it.
There were several groups that have tried to do this. Intel has been the first one to demonstrate this in silicon.
Today, optics is a niche technology. Tomorrow, it's the mainstream of every chip that we build.
They've demonstrated the Raman effect in silicon, meaning that as photons come in from a light source, they're actually able to amplify those photons and focus them into a coherent beam of light that can be used as a laser source for optical communication.
This breakthrough, which is the first ever continuous silicon laser, is significant because it's the first time that inexpensive, very pervasive silicon has been used to make a laser. Today's optical devices are built out of exotic and rare materials like gallium arsenide, indium phosphide, very difficult to say, even harder to manufacture.
Intel's device was made using standard CMOS manufacturing in an existing fab. That eliminates any doubt that this technology is manufacturable. Typically, the path between the laboratory and the factory is a long and painful one. That is not the case here.
This significant breakthrough really meant overcoming a key challenge. We were able to early on achieve pulse lasing, which is an interesting physical effect in silicon, but it was not the kind of effect that would allow us to apply this to real-world applications. To overcome that, we had to get by an effect wherein photons were absorbed by the electrons in the substrate and thereby shutting down the lasing after that brief pulse. We were able to apply strong fields across the channel and as a result almost vacuum sweep the electrons that were causing the problem out of the channel. We've demonstrated that you can take silicon and laze with it. And that's an opening to allow photonic technology to be applied to a whole realm of things that previously it just didn't apply to.